today's video, I would like to talk about creating Taylor series. So Taylor series is probably a new word for you. We just finished talking about power series. Now, power series revolved around generating series to represent functions for certain intervals of convergence. And the main formula that we had is f of x equals 1 over 1 minus x equals the sum from n equals 0 to infinity of x to the n. Now, this was great, and it allowed us to generate a lot of power series for different functions, but we needed to mold it to create this form. So that restricted us a little bit. But now we're going to generalize it with the idea of a Taylor series. So Taylor series is really the general idea of a power series. It allows us to replicate pretty much any function that we want as a infinite series. So how do we do this? Well, I'm just going to give you the formulas right now for how we do it. But essentially, in order to form a Taylor series, we take advantage of the derivative. And when we do this, we can generate any function, f of x, by taking the sum from n equals 0 to infinity, 1 over n factorial times f of n times the nth derivative of f at a times x minus a to the n. So what this does is this centers a Taylor series at x equals a, and we take the sum of derivatives and divide it by n factorial. Now this is just an application of the power rule of the derivative that we're exploiting here. What we get is immediately you can see we get our intercept, or we get our functional value at a, then we also get a linear approximation at a, and then we get a quadratic approximation. So in Unit 2, we talked about the idea of a linear approximation, but now we have a quadratic approximation that we take the second derivative for. And obviously we get cubic and quartic and quintic approximations as well as we keep adding. But essentially this we have here that's shown without the dot 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 is a second order Taylor polynomial, which is an approximation, a quadratic approximation for f of x at a. So that is how we find that. Now we also have a special case for a Taylor series called a Maclaurin series. Now Maclaurin series is the case where we center our Taylor series at 0. So to do this, we get f of x equals the sum from n equals 0 to infinity of 1 over n factorial nth derivative of 0 times x to the n, which should be something that is not too hard to understand. Instead of centering at a, we're centering at 0. We get f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared, all the way to wherever you want. So let's try making a Taylor series. So I'd like us to determine a Maclaurin series for the natural exponential. So this means finding a series that represents the exponential, which looks something like that, at this point, at x equals 0. So how do we do this? So really the only thing that we need to know, because we know it's centered at 0 already, we know the formula for the Taylor series, we just need to determine the nth derivatives. So what are the nth derivatives at 0 for e to the x? Well, we know that if I take any derivative of e to the x, I get e to the x. So any nth derivative of e to the x evaluated at 0 is going to be e to the 0, which is 1. So because I know this, I can now say that any nth derivative of e to the x at 0 is going to be equal to 1. So I get the sum from n equals 0 to infinity of f nth derivative at 0 over n factorial times x to the n, which is equal to the sum from n equals 0 to infinity, in our case, of x to the n over n factorial. So this is the power series for e to the x. And this is obviously 1 plus x squared over 2 factorial plus x squared over 3 factorial, x cubed over 3 factorial. We keep going on and on. So that's how we generate the e to the x Maclaurin series. Now let's check its radius of convergence. So I take the ratio test. I do a sub n plus 1 over a sub n absolute value. Of course, we get something that cancels out quite nicely, and it gives us the absolute value of x over n plus 1. Taking this limit, obviously, I just get 0, because for all x, because as this goes to infinity, well, it goes to 0, and we have that plus 1 down there. And 0 is always less than 1, so it satisfies the ratio test. So actually, the radius of convergence for this Maclaurin series, e to the x evaluated at 0, is infinity. So we have found a perfect series representation for e to the x. So that's how Taylor series works, and you can fiddle around with this for all of the functions. At the end of this unit, we'll generate like a bunch of different formulas for all of the ones that you need to know, but that's how it works. In the next video, we're going to talk about how to estimate remainders for these series. As you noted, we generated an infinite series, but I could have taken just these terms. Then I'd want to know the difference between this quadratic approximation for e to the x and e to the x. I'd want to know that difference. So we'll talk about that in the next video. Thanks for watching.